Hey there, in this video I want to talk about Fourier filtering and smoothing. The basic idea here is we're going to start with some data that has a whole range of frequencies in it, and we are going to Fourier transform it and then discard some of those frequencies. We could choose to discard just the high frequencies or just the low frequencies. These are creating low pass and high pass filters. Or we could discard frequencies that have small coefficients and are not that important. That would be called Fourier smoothing. But so the two techniques are pretty closely related. The idea being that we throw away some frequencies, and then after we've done that, we do the inverse transform to recreate data that is either lacking high frequencies or lacking low frequencies or lacking frequencies with small coefficients and just showing you the dominant frequencies. Now let's do an example with the filtering. We're going to create a low pass filter, meaning we only want to keep low frequencies from data. So I'm going to start by making up some data here. We'll create some x values that we'll do in the range 0 to 1. We'll make 100 of them. And then for our y data, let's make some kind of noisy sort of sine function. So we'll do sine of 2 times pi times x. So that should be like a frequency of 1 hertz, plus 0.2 times np dot cosine 20 times np dot pi dot x times x. Okay, so this should have 2 frequencies in it. It should have 1 hertz and 10 hertz. And we're going to do a low pass filter so that we're only keeping the lower frequencies. Now we're going to sample this data. So, it's not exactly this function. It's a sampling of this function. And like we saw before, it's not going to be an exact match. That doesn't really matter, though, for what we're doing here. So I'm going to calculate the DCT using FFTPack.dct. I could do this with an FFT as well. The nice thing about the DCT is that I know the results are going to be real. And it's a little bit safer when throwing away coefficients if they were all real. What you can run into when you throw away coefficients from the FFT is you have to make sure you're discarding them so that they are symmetric around the Nyquist frequency. If you don't discard your coefficients symmetrically around the Nyquist frequency, then you'll have complex contributions left over and you'll turn your real function into a complex function. And that's usually bad. So we're safer here using a DCT for that reason. Remember, we always have to attach norm equals ortho because reasons. I don't know. For whatever reason, the way they wrote this library was like the default choice is not ever what you want. Okay, so now here's the magic. I'm going to take any coefficient after the 4th, including the 4th, and set it equal to 0. Oof, gone. And so now my smoothed is going to be the result of doing an inverse transform, in this case an inverse DCT. And we'll do that to the now modified DCT. Again, make sure you do this norm equals ortho. And let's check it out. So I'm going to plot the original data. We'll do that as dots. And let's also plot the smoothed. And I'm just doing this element by element here. We can make this as a function of x. Why don't we do that? That's not hard. I was thinking we were in frequency space, but we're not. We're in real space, so we can do x and y. Okay, let's see what we get. So here's the underlying data, is the dots, and you can see it's got this high frequency component to it, and we've thrown away low frequency terms. Now to get a sense of like what has just happened there, let's modify our code a little bit and let's print the result of the original DCT. Okay, so here's our original DCT, the low frequencies up through high frequencies, and we can see in this case, like this frequency is kind of tiny, but this one's pretty big, 6. It's tiny, this one's kind of big, this one's tiny, and they're all kind of tiny from here on out. So we got 0, 1, 2, 3. We kept all of those, and then 4 through the end, we set all of these equal to 0. So we get a little bit too ambitious here, and we set like almost everything equal to 0, and then plot it. It doesn't work very well. Don't get too carried away here with throwing away your frequencies. So we could also make this value larger, meaning we're turning off less of our array, and doing that doesn't make too big a difference. So we could do first 20, or first 10, keeping the first 10, first 15, maybe first 50. Okay, so at some point it starts getting pretty wiggly here, and I'm making this look like trial and error, but it's really not quite trial and error, because we can look at the original coefficients in this array, and what we're going to see here, somewhere between 20 and 30, 25, 5 still good, but 20 smooth, 25 is not smooth. Okay, we're getting in there. Somewhere in the 21. Okay, and if we go and count into our array, so 0, 1, 2, 3, so basically it's 4, right? So 4, 8, 12, 16, 20. So it'd be like somewhere in this row. Look right there. There's another big coefficient. And then after that, there's just no other big coefficients. This corresponding effectively to that 10 hertz signal.